So in this video, we will learn about parallel circuit. So let's say we have this circuit with two resistors connected in parallel. And our applied voltage is 24 volts and we have 6 ohms and 8 ohms resistor. Now the question is, how can we calculate the current that is flowing in its resistors? So before that, we need also to know that in parallel circuits, the voltage drop across each resistors connected in parallel is the same. So in this case, it is 24 volts. We have the low potential difference, which is 0, and on the top, which is 24 volts. So here in this case, voltage drop across 6 ohms and 8 ohms is equal, which is 24 volts. So actually, we can describe the flow of current in parallel circuits as an analogy of a river, because electric current will flow from high potential difference to low potential difference. So as an analogy of water or river flowing in the water is flowing from upstream to downstream. So water will not flow from low stream to upstream. The gravity will pull it down. So the same with electric current. Current will flow from high potential difference or from high voltage to low potential difference, which is in the case in our example 24 volts to 0 volts. Okay. So let us solve for the current across each resistors. So how can we solve this one? We can use the formula V is equal to IR. So we all know that the voltage supply is 24 volts and the resistor 1 is 6 ohms. So we can now have 24 divided by 6, and that is 4 ampere. So there is a current that is flowing on 6 ohms resistor, which is equivalent to 4 ampere. And how about for the 8 ohms resistor? So we can still use VIR, 24 I multiplied by 8 ohms resistance. So the current is equivalent to 24 divided by 8, and that is 3 ampere current. That is also flowing to 8 ohms resistance. Now another question is, what is the current that leaves from the battery? So the current that leaves from the battery actually is equal to the sum of the three current flowing to 6 ohms and 8 ohms resistor, and that is equivalent to 7 ampere. Yes, it is 7 ampere. It is true. According to Kirchhoff current law, a current entering from a circuit is also equal to the current leaving in the circuit. So let's say, for example, in this case, we have this branch. So there is a current flow. There is a current that will flow in 6 ohm resistor, and also there's a current that is flowing in 8 ohm resistor, which is 3 ampere rather. So the current flow will flow from here, and also there's a current that will go down. There's also a current that will go here. So the current will enter to this branch. The 7 ampere current will enter to this branch, and also another current that will go out to this branch, and also this 4 ampere will go out to this branch. So actually in the end, it will sum up to 7 ampere current. So this is true according to Kirchhoff's current law, that the current entering is equal to the current leaving. So in this case, we have 7 ampere. Now, next thing to do is to calculate or to determine the equivalent resistance of the circuit. The equivalent resistance of the circuit, or the total resistance of the circuit. Still, we can use VIR to solve for the equivalent resistance. So we have 24 volts, and the total current that is flowing in the circuits, which is equal to 7 ampere, and the equivalent resistance. So we have now 24 volts all over 7 ampere. So we can have R is equivalent to 3.43 ohms. Notice that this 3.43 ohms is less than to each resistors 6 ohms and 8 ohms. It is, yes, it's true. It's because as you add more resistant or resistor in a connected in parallel circuit, the total resistance decreases. It's because there is um it's because there is a lot it's because there is more current that will flow in a parallel circuit. As you add more, or as you add new branches, there is more current that will flow, that can flow in the circuit. So in case of series circuit, as you add more resistance, the total resistance increases while the current decreases, because there is no enough current that will flow in the circuit because you add more resistor. So the total resistance increases and there is a less current that will flow. However, in parallel, as you add more resistor connected in parallel, the total resistance decreases. So as you observe, the total or the required resistance here, or the equivalent resistance here rather, is less than to 6 ohms and 8 ohms. Now, the second step is we can use this formula, 1 over RT, 1 over R1 plus 1 over R2 to the negative 1 to the negative 1. So we have RT is equivalent to R1 plus R2 to the negative 1. So this is another way to solve for the total resistance RT, or it is equivalent to REQ. So we have 1 over 6 plus 1 over 8 to the negative 1, and as you use our calculator, this is equivalent to 3.43 ohms. So they are equal. Okay, now our next step is to determine the power delivered by the battery, by the 24 volts battery. So to solve for the power, we can use this formula. P is equal to IV. So we have I, which is 7 ampere, and the voltage supply of the circuit is 24 volts. Then we have 168 milliwatts. So 160 milliwatts is delivered from the battery for the circuit. Now, next thing to do is to determine the power absorbed by its resistors. So we will use the other formula. P is equal to I squared R. So the voltage or the power that is absorbed from 6 ohms resistors is equivalent to 4 ampere. So the current flowing on this resistor, and the 6 ohms resistance, and that is equivalent to 96 milliwatts. For the second resistor, we have, let's use the other formula, V squared over R. So we have, since the voltage across, or the voltage drop across each resistors connected in parallel is the same, so in this case, so we have 24 volts squared over 8 ohms resistance. So power is equivalent to 72 milliwatts. So we have 96 milliwatts here, and we have 72 milliwatts. Notice that this 96 and 72 milliwatts will sum up to 168 millivolts power delivered from the battery. So that's it. So this is how we are going to solve for uh, parallel circuit. So let's have one more example. So let's say we have this circuit, and this is equivalent to 2 ohms, 5 ohms, and 10 ohms. And let's say, for example, we have 24 volts supply. So in parallel circuits, as we've discussed earlier in the previous example, the total voltage uh, of the parallel circuit is equal to the voltage drop across each resistors connected in parallel. So in this case, we have um, 24 volts. So voltage drop across 2 ohms resistor, 5 ohms resistor, and 10 ohms resistor is equivalent to 24 volts. So it is very important that we know these properties in parallel circuits in order for us to be guided in solving for the current, or for solving for the current across each resistor. So let us now solve for the current across each resistor. So we can use the VIR formula. So we have 24 volts is equal to I, and the resistance across the resistance across the first resistor, which is 2 ohms. So we have I, so 24 divided by 2, this is equivalent to 12 um, ampere. And for the other current flowing in 5 ohms resistor, we can still use VIR. So that is 24 equal to current and 5 ohms resistance. So the current is equivalent to 24 divided by 5 ohms, and that is 4.8 ampere. And the other one, we have 24 volts, 10 ohms. So 24 divided 10 ohms, that is equivalent to 2.4 ampere. Okay. So to solve for the equivalent resistance of the circuit, we need first to know also the total current that is flowing in parallel circuit. So in this case, in parallel circuit, the total current is equal to I total 12 ampere, or we can say I total, this is IR1, so the current across resistor 1 plus IR3 plus IR1, IR2, IR3. So we have 12 ampere plus 4.8 ampere plus 2.4 ampere. So the total current is equivalent to, let's compute in the calculator. So we have 19.2 ampere. So there is a current that is flowing in our circuit, which is equivalent to 19.2 ampere. So we have here 12 volts that is 12 ampere that is flowing in 2 ohms resistor, and we have 4.8 ampere and again 2.4 ampere. Okay, so there is a current that will enter on this branch, and there is also a current that will also that will go out from this branch and will enter to this branch again. So according to Kirchhoff's current law, the current entering on the circuit is equal to the current leaving on the circuit. So as you can see, it will add up to the 4.8 and 2.4 ampere will add up to 19.2 ampere that is entering from the branch of the circuit. So to find for the equivalent resistance, we can use the VIR formula, since we already have now the total current that is also flowing in the circuit. So in this case, we have 19.2 as the total current. So let's resize this one to have more space. Okay. So for the equivalent resistance, we have V is equal to IRQ. So we have 24 volts. Current is 19.2 ampere. Then REQ. REQ now is equivalent to 24 volts all over 19.2 ampere. So REQ is equivalent to, that is equivalent to 1.25 ohms. Actually, you can also compute using this formula 1 over RT, 1 over R1 plus 1 over R2 plus 1 over R3. So multiplied with the power of -1. So we can have RT is equal to 1 over 2 ohms plus 1 over 5 ohms plus 1 over 10 ohms. So we have 1 over 2 plus 1 over 5 plus 1 over 10. So we have 1.25 ohms. So this is the same with our previous example. So as you can also observe, the total resistance is less than to the resistance of each resistor. So RT is less than 2 ohms, RT is less than 5 ohms, and RT is less than 10 ohms. Again, it is true because as you add more resistor connected in parallel, the total resistance decreases while there is enough current that will flow or that will light your bulb. So there is always enough current. So as resistance, total resistance decreases, current increases. Okay, so that is the idea for parallel. So let us compute for the power delivered by the battery, by the 12 volts battery. So we have PIV. So power is equivalent to the total current. So we have 19.2 ampere multiplied by the voltage, which is equivalent to 24 volts. Power is now 19.2 times 24. So that is 460 watts. So we have 460.8 watts that is delivered from the battery. So for the power across each resistor, we can compute using again the same formula. So we can have P IV. So we have power across resistor 1 and the current across resistor 1, which is 12 ampere times the voltage, which is 24 volts. PR1. So we have 12 times 24. That is equivalent to 288 watts. So we have 288 watts. So for the second current, we have PIV. Power is 12 ampere current times the voltage. Yes, 12 ampere. No, not 12 ampere. Rather, the current across resistor 2 is equivalent to 4.8 ampere. So 4.8 ampere multiplied by 24 volts. So we have 115.2 watts. So for the other last one, we have still VIB. So we have the current across resistor 3 is 2.4 times 24 volts. So we have 57.6 watts. So notice that if we will add this 3 power that is absorbed from each resistor, so it will add up to 460.8 as the total power or the power that is delivered from the battery. Okay, so that's it. So always remember that power is the rate of change of energy per unit of time, as power is equivalent to 1 joule over per unit of time. So that is 1 watt. Okay, so that's all. Thank you.